Hello class, welcome to Algebra Lesson 6.3, which is all about exponential growth and decay. By the end of this lesson, you should be able to use exponential functions to model situations and make predictions. So let's jump right into it. Example 1, exponential growth. If you look, I have the exponential function that we worked with yesterday written right here, just to remind you, f of x equals a times b to the x power. Today we're going to be working with the exponential growth function, which looks pretty similar, but instead of b, I'm going to use 1 plus whatever the rate something is growing by, okay? So let's read the problem. The population of Hillville grows at an annual rate of 15%. What will the estimated population of Hillville be in 5 years? So if we look at the sign, we have welcome to Hillville, and the population is 5,000 people. So A, remember, represents our initial population. So I have f of x equals 5,000 times 1 plus, and then r, I said, represents our rate. Our rate is whatever percent something is growing by. So 15% written as a decimal, because we always convert our percentages to decimals when we're working with them, is 0.15, and then x represents time in years, okay? That is something really important to remember. Sometimes you'll be given a problem that says 36 months. If you were given something that said 36 months, what you would have to do is say 36 divided by how many months in a year? 12. So 36 divided by 12 is 3. So instead of using 36, you would use the number 3 to represent 3 years. So always be watching out to make sure that the time frame you're given is already in years, and if it's not, change it to be written in years. Okay, so I have my function, it's written out. I'm going to simplify things a little bit before I try to pull out my calculator though. I'm going to leave that 5,000 just like it is, but I'm going to change that 1 plus 0.15 to be a 1.15x, okay? Now, if I were to look at this problem again, what is x going to represent? At the end of the question, we were told 5 years, so I'm going to replace that x with a 5. Now I can type this into my calculator just like it's written here. The only thing that I would have to change is after I type in 5,000, parentheses, 1.15, parentheses, in order to get that 5, I'm going to have to use my caret key and then hit 5. And your calculator, so the TI-30X, is smart enough to know order of operations. It knows that it has to do that exponent first. So your calculator is going to start by multiplying 1.15 to the 5th power before it multiplies by 5,000. So if you don't have a calculator strong enough or powerful enough to do that, you want to make sure that you do the 1.15 to the 5th power first before you multiply by 5,000. But when I do that, I am left with a number of about 10,056 people, 0.79. But I don't like to have 0.79 of a person because that's not possible. So I'm going to round, instead of 0.7, that tells me I'm going to round up to 10,057 people. And that will be my answer for this problem. Okay, if you have questions about that, please reach out for some help. I am happy to help you. All right, jumping into the next idea, compound interest. Well, first of all, let's just talk about interest. We have interest is calculated in 2 different ways, simple interest and compound interest. Simple interest is interest paid only on the principal. For those of you that are thinking, what on earth is a principal? That's like the person that rules our school, right? No, well, yes, but principal here talks about our starting amount, okay? So compound interest is the interest paid both on the principal, the starting amount, and on the interest that has already been paid. So the compound interest formula is a type of exponential growth, which is why we're going to talk about it. So our compound interest formula is represented right here. We have A, which is the amount paid, equals our principal times the quantity of 1 plus the rate divided by the number of times per year the interest is compounded, all raised to the number of times it's compounded times the time in years. Okay? And if we look and compare, if we started with $10 and we had a 5% simple interest rate and a 5% compounded quarterly interest rate, you can see that over time, the compound interest actually earns more money. It gets you more money for your value. So compound interest can be a really, really good thing. Some key words that I notice that students sometimes struggle with is knowing what like annually means. So annually means that it is compounded once per year. Biannually or semi-annually means it is compounded 2 times per year. Quarterly means 4 times per year. Monthly would be 12 times. And daily, we're going to assume it's not a leap year for those problems, unless it is stated otherwise, so we will use 365. If it said weekly, you would use 52. Okay, so make sure you know what these words are, and make sure you, study this formula here, because when it gets to be the test, I can't answer any questions about what these variables represent or what annually, biannually, semi-annually, what any of those words mean. Okay, because that's what I'm testing you on. So I recommend maybe make some note cards and start studying before our test. All right, example 2, exponential models of growth. Kimberly's family invested in a certificate of deposit, or CD for short, for her when she was born. The interest compounded quarterly. So remember, quarterly means 4 times per year. The amount deposited was $3,000. That's going to be my p-value. The annual interest, that's my r. It was 8% and compounded quarterly. So remember, our formula from the last page is the principal times 1 plus the rate over the number of times it is compounded, raised to the number of times the number of years as the exponent. So let's fill in our variables. So the amount would be equal to the principal, which was 3,000. Then I'm going to say 1 plus my rate is 8%, so 0.08. Compounded quarterly, that's 4 times, so 0.08 divided by 4. And then I'm going to say compounded 4 times the number of years, which we were told just now is we're looking at 5 years. Okay, so if I simplify this a little bit, 3,000, and then 0.08 divided by 4 is 0.02. So I'm going to say 1 plus 0.02, that's just 1.02. And then 4 times 5 is the 20th power. So I'm going to type that into my calculator, and when I do that, I am left with $4,457.84. Okay, so that's how much money the CD is worth at the end of 5 years. So you can see that Kimberly has earned almost $1,500 in just 5 years from the starting amount. Letter B, will the value of Kimberly's CD be greater after 15 years if it is compounded annually? So remember, annually means 1 time per year rather than quarterly. So we want to know if it's compounded once per year, does she earn more money? So let's first figure out our quarterly, since we already have a nice formula for that. So quarterly means that I would type in, let's see, the amount started at 3,000, and we already determined that 0.08 divided by 4 is 0.2, and then we would have 4 times, instead of 5 this time, I'm going to say times 15. And 4 times 15 is 60. So I'm going to change that. When I plug that into my calculator, I'm left with $9,843.09. Now let's figure out if it's compounded annually, how much money would she get? So again, my starting amount hasn't changed. I start with 3,000. I'd say 1 plus 0.08 divided by 1, because annually means once per year. Well, anything divided by 1 is just itself. So I have 1 plus 0.08. So I'm going to just combine those right now. I'm going to say 1.08 raised to the and then it's once per year for 15 years. 1 times 15 is just 15. So if I type in 3,000, parentheses 1.08, caret 15, I am left with $9,516.51. So which one did she earn more money with, the annually or the quarterly? She earned more money with the quarterly. And in any example, if you keep the starting amount the same, the interest rate the same, any example that's compounded the most means that person's going to earn more money. Okay, so if it's compounded 4 times, that's going to earn more money than 1 time. If it's compounded 12 times, if we say it's compounded monthly, that's 12 times, that's going to earn more money than even the quarterly. Okay? So, question number 2, what will be the difference after 15 years if the CD is compounded semi-annually rather than quarterly? So just a reminder that quarterly on the last problem earned $9,843.09. So you want to figure out how much money is earned when it's compounded semi-annually, and what's the difference between those two. Good luck. Okay, so when you solve this problem, hopefully for the semi-annually, you ended up at $9,730.19. And when you figured out the difference, remember difference is another word for subtraction. So I did my quarterly minus my semi-annually, and I noticed that my semi-annually earned $112.90 less than the quarterly compounded interest. All right, so we've talked about exponential growth. Let's talk about exponential decay. So exponential decay is going to work pretty much the same as our exponential growth with one very important difference. You have your A value times 1 minus that rate rather than plus. Okay, so I have 1 minus r instead of plus and raised to the x power. Okay, so we have a video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views the video has decreases by 25% each day after that. In how many days will the video stop being a fan favorite? Okay, so let's start plugging in information we know. A always represents our starting value, so 8,192 times 1 minus, remember R represents your percentage as a decimal, so 25% as a decimal is 0.25, and then x power, so 8,192 times 0.75 raised to the x power is going to be my function. Now, you can see over on the right we have a couple of days already calculated out. We have a graph that's already calculated out. We want to figure out when is it going to reach below 1,000 views. Unfortunately, you guys don't have a super powerful calculator, so that means that you have to do a little bit of guesswork here. So what I'm going to do is I'm just going to start with, let's say, we know that 3 days, based on this table, is 3,456. Let's skip 4 days and let's check out what happens if I plug in 5 for x. After 5 days, I'm left with 1,944 views. So if I plug this x, if I change that to a 5, I get 1,944. If I look at that, 1,944 is still quite a ways above 1,000. So I'm going to skip the number 6 and let's try 7. So if I plug in 7, I'm left with 1,093.5 views. So I'm still above that 1,000 threshold, but I'm close. So let's see what happens if I plug in 8. If I plug in 8, I am left with 820.125 views. So I know that after 8 days, it drops below the fan favorite. 8 days. So that would be my answer. Okay. If when you plugged these numbers in, you did not get these numbers out, so when you plugged in 5, if you didn't get 1,944, please ask for some help on how to plug things into your calculator. All right, question 3. Suppose the number of views decreased by 20% per day, and how many days will the number of views per day be less than 1,000? Good luck. Okay, for this problem, hopefully you set up your function as f of x equals 8,192 times 0.8 raised to the x power. Then when you plugged in numbers, hopefully you found that after you plug in 10, you drop below 1,000. Okay? When you plug in 10, you get 879.6 views. So that is our first number that's below our 1,000 threshold. All right, example 4, exponential models of decay. The number of pica in a region is decreasing. How does the decrease in the pica population for years 1 to 5 compare to the population for years 6 to 10? So first let's write a function. We're talking about exponential decay. So again, a times 1 minus r raised to the x power. A represents my starting value, which my initial population of the picas is 144. And then R represents the rate of decrease. In this case, it is 8% each year, so 0.08. So if I were to simplify this, 144 times 0.92 raised to the x power, f of x equals 144 times 0.92 raised to the x power. All right, now what I'm going to do, since I was told to find I want to compare years 1 and 5, like that range, to the range of years 6 through 10. So what I'm going to do is I'm going to plug in, instead of x, I'm going to plug in 1. And when I plug 1 into that equation, I am left with about 132 picas. If I plug 5 into that equation, I am left with about 95 picas. So I'm going to find the rate of change between those. So 95 minus 132 over 5 minus 1. I got the 5 and the 1 from the years, and 95 and 32 from the number of picas left. That's about a decrease of 9.25 picas per year. If I compare years 6 through 10, when I plug 6 in, I get about 87 picas. When I plug in 10, I'm left with about 63 picas. So if I do 63 minus 87 over 10 minus 6, I'm left with about negative 6. So you can see as the years go on, the rate of decrease lessens, right? Because negative 6 is not as steep of a decrease as that negative 9.25. So for years 1 to 5, the pica population decreases by an average of 9.25 picas per year. And then for years 6 to 10, the pica population decreases by an average of 6 picas per year. The average rate of change for the pica population decreases as years increase. Okay? Okay, and then here I have our concept summary. What you need to make sure you start studying, start memorizing all of these different formulas, okay? I will not be able to answer questions on what any of those variables mean, how to set any of those up, how to solve those. That's what I will be testing you on. That's why you want to make sure you start practicing, start memorizing these now, so that way you're asking questions now while I can answer them, okay? So if you have any questions at all, please feel free to reach out for some help. I'm happy to help you. Have a great day.